All right, so this was fun. Let's talk about the next item. We have this lab we did where the graph looks something like this. This part right here. Let's go ahead and erase this part that's not obvious. And while the graph was like this is when it was. This is when it was steam and water. And this was ice and water. So when you are watching a particle, the particles are sitting there, let's say it's steam and water. You've got these springy, elastic bonds between the molecules of water because it's water, so it's a liquid. These things are moving faster and faster. They're shaking faster and faster. These are shaking faster, shaking faster, 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 faster. There's a limit. There's a limit because they're held together. And because they're held together, they can't move any faster. Any faster, those bonds would break. So what happens here is, when this graph was being done, this was temperature, this is how fast average kinetic energy of particles, and down here was time, but really it's heat, because I'm going to keep putting heat into it. And so why does it stop the particles moving faster and faster? Because I'm putting the energy into moving faster and faster. They're not moving faster and faster. They stay at, and your lab was probably about 92 degrees. We're going to pretend like it's 100 degrees, because that's what it is at sea level. So these particles move faster and faster, faster and faster and faster. And at some point, they just need enough energy so they can break loose. Because once they're free of each other, they can go as fast as they want, right? There's no stopping them at that point. But it takes some energy to break these bonds because they're attracted to each other. So somebody's got to pull them apart, and that requires some extra energy. Because it requires extra energy, that energy should be measured. Okay, and so this is the idea of heat of fusion. Okay, heat of fusion says, or heat of vaporization in this case, heat of fusion says the amount of heat necessary to change 1 gram, didn't work. Heat of fusion is the amount of heat, can't write very well, so I'm on this little pad, of heat necessary to change, man, that doesn't look like change at all, right? Change instead of whatever I just wrote there. To change 1 gram of a solid into a liquid, right? And so that's an amount, okay? And so that's what heat of fusion is. It is measured in, the formula for it, which is right here, is H equals mass times heat of fusion, okay? And heat of fusion is measured in joules per gram, how many joules of heat it takes to make 1 gram melt. This is our old friend mass, which is measured in grams, and then heat's the amount of heat necessary to make something happen. A similar thing happens for heat of vaporization. And that is the amount, so I can write better this time, sorry, of heat necessary to change 1 gram of a liquid into a gas, okay? And its formula is going to look just like that one. It's going to be H equals MHV, joules per gram it takes to heat it. And then I've got my grams for my mass. And again, this is the heat that's necessary to make it happen. This is my outside source. All right, so let's go ahead and play with this very first one. Here we go. I'm going to play with the first one. Select. Crank this out. Hit delete. And so this is a fairly straightforward formula. What does it mean? It says a 40-gram sample of chloroform is condensed from vapor, means gas, into a liquid at 61.6 degrees. So both are 61.6 degrees. So apparently that's the boiling point of chloroform. Right? It's the boiling point of chloroform. So liberating 9,870 joules of heat. what is the heat of vaporization for chloroform? Well, heat necessary to liberate it, or to condense it, as it were, is equal to that. Okay? So the heat is 9,870 joules. The mass of the chloroform is 40 grams. And it asks us what the heat of vaporization is, so I can solve for it. Okay? Quick divide it across the inside. 9870 divided by 40. The heat of vaporization, in this case, would be equal to 246.75. Now, this is only good to 3 digits. This is only good to, I can't find it, 3 digits is 40.0. So this can only be good to 3 digits. So 247 units. Now, if you want to cheat, you can always use the chart. On the chart, it has to tell us. So this is our heat of, this is our heat of vaporization here. It's measured in joules per gram. 70 joules per gram, and I'm done. So that's how many joules per gram it takes to heat. So for every 247 joules of energy I pour in, 1 gram of chloroform would turn from a liquid to a gas. All right, that's not bad. Now, here comes the scary, hairy news. Read the next problem. We'll jump on it in just a second. Go ahead and pause it and think about it for a second. So if you looked at it for a moment and said, what am I going to do with this thing? So the answer to the question is you're going to do the lab. What? Okay, so think about this. Here's my pen. Here's my pen. So what we're going to do is we're going to say, look, this thing is starting as ice. And as ice at negative 30 degrees, it can't melt. It can only melt when it gets to 0 degrees. Once it gets to 0 degrees, it's going to go flat until it all becomes water. And then after that, it's going to start changing temperature radically upwards until it starts boiling. And then it's going to become a gas. But as long as there's water around, the temperature is still going to be 100 degrees. We need to get to 100 degrees, so it's going to go up again until it gets as gas. Okay? Which means, and during this problem, the following things are going to happen. The heat for the outside world is going to, first of all, change the temperature of the ice. Change temp ice. Then, once it gets to the boiling point, it's got to melt the water. Well, melting, so we're going to melt. Then, once it's done melting, it's going to change temperature as water. So, change temp water plus, once it gets to here, it can't go past 100 degrees, so it's going to stop, and it's going to start to boil, turn a liquid into a gas, plus, once it gets to the end, it's going to start changing temperature again, so it's going to change temp as gas. So we're going to notice that when it's changing temperature as ice, it's going to start at the starting temperature, which was negative 30 degrees, so negative 30 degrees until it gets to 0. Why does it stop at 0? Because that's the point at which it melts. It can't go past that temperature. Ice above 0 degrees doesn't exist. Now you can see it on the side of a road above 0 degrees. Why? Because it hasn't melted yet. It still has to heat up. But the temperature of the ice at that point is 0, even though the temperature of the air might be much warmer. Okay? And then when we change temperature of the water is going to start at 0 degrees, because that's where the ice changes. And we're right here, our temperature is not changing. And then it's going to get up to 100 degrees. I always stop there because that's where it boils. It's going to boil, and then it's going to start at 100 degrees, and it's going to get itself up to 120 degrees because that's what the problem says right here. Maybe not. My pen. It says right here. Okay. So, next step, putting in all the equations. Okay? So putting all the equations. Well, first of all, is there heat coming from the outside world? The answer is yes. It's how much heat is coming in. So, heat equals formula for changing temperature ice. Well, that's mCT minus T naught. Changing temperature, everything, right? Next one. What's our melting formula? Oh, that's our heat of fusion problem, and that's going to be at mass heat of fusion. That's how much it takes to melt some ice. Plus, and then I have change in temperature of the water. Well, it's change in temperature. Use my change in temperature formula. Also, I'm going to use my boiling. I need to boil it now. So if I'm going to boil it, it's going to be M heat of vaporization plus, and then you change the temperature again, is going to be the same formula it was for the other things. Heat to the outside world, don't know the number for that. What's the mass of the ice cube? It says 1 kilogram, so that's 1,000 grams. Specific heat of ice. Now remember, that's not water, ice. Ice is actually easier to heat up, so it's 2.060. Final temperature of the ice. Now it's only the ice. I know this thing's going to end up at 120 degrees, but it stops being ice at 0, so that's where we stop the ice. Minus 30 plus mass of the heat for the heat of fusion. Well, the mass of ice I want to melt is 1,000. Heat of fusion. Now it's got to be on this table because I'm not memorizing these things, and there it is right there. Heat of fusion of ice is 334. Plus, now I've done these two right here. I got to do this next one right here. MCT minus T naught. So how much water do I have? Well, I have to start with 1,000 grams of ice. That's got to be 1,000 grams of water. There's no option here. Specific heat of water, again, written on the chart, 4.180. Final temperature of the water is going to be 100. Initial temperature is going to be 0. Plus, now I've done this one. Now I got to do this one here. What's the mass of the water? Well, it's 1,000 that I want to boil. HV would be heat of vaporization. How hard is to boil something? And right here it says 2260. So 2260. I'm running out of space, so let me bring this down here. It should have been plus 1,000 times 2260 times final temperature, which is 120. Oh no! Oh no! I'm doing something wrong here. Okay, so I got 2260 was the heat of vaporization. Now I got to do this one. Now I'm doing this one. My bad. So I do I'm going to do changing temperature, right? So I do changing temperature. So it's going to be MC T minus T naught. Right, from here. It's going to be this formula right here, MC below. So I got 1,000. Specific heat, C, is going to be for steam, is going to be 2.20, sorry. And then I have the final temperature is going to be 120. Initial temperature is going to be 100. And the rest is just slap it in your calculator equals. Shouldn't be that bad. Should be good. Now, this is a nightmare problem. If you can do this problem, you can do all the rest of the problems. If you can't do this problem, come see me for help because this is the hardest part of the chapter, I imagine.